So this is a paper by GECKO, Maggie, Varela, presenting here today, and Sergio. So,
thank you so much for your introduction. I hope you can hear me also without the microphone. This is a work that is contextualized in the business process management field. The business process management field is a research and a practical discipline that focus on understanding how work can be performed in an organization by managing and optimizing the business processes of an organization. A business process basically is a set of activities that are performed to realize a business goal. And a business goal is the objective that an organization aims to achieve. Usually, a business process is represented through a process model, where the process model is
better?
Yes.
Okay, quite better. So a process model basically is the structure of the process. So the structure that is in charge of organizing the execution order of process activities. In the business process management world, the most used notations for representing process models are imperative models notation. In particular, all these notations are based on a subclass of patronets. And from patronets, we have several imperative notation like Wolfram-Nets, BPMN, the business standard notations, and so on. An imperative process model usually is able to represent explicitly the full process behavior at once. So we have explicitly to put all the activities and the execution order of all the activities in the process model. In the last year, there was a growth of other kinds of process model, called declarative process model. In this case, the execution order is not made explicit in the process, but is determined by the use of constraints. Constraints basically implicitly specify the allowed behavior of the process. The idea of the declarative process model is that every task can be performed except the ones that do not respect the constraints. Here, for example, it is an example of a declarative process model. This line means, for example, that A is performed. If A is performed, B must be performed no matter before, after, or B. This is another constraint, for example, that says that whenever B is performed, C must be performed afterwards. We will see this language in the next slide. So the idea is that we have constraint to represent the structure, the process model. Why declarative process model? Because declarative process models are very good to describe dynamic environments where processes are highly flexible and can be subject to changes. So in this last year, there was really a growing of usage of this kind of model for representing processes in the business and non-conventional business domains. In the field of business process management, one of the very hot topic now is called process mining. The idea of process mining is this one. So we have several process models, imperative or declarative, that describe the behavior of the process. We have several event logs, so data, information that represent the concrete execution of the process. So how the process has been really executed in practice. Process mining try to, let's say, compare this real execution, the event logs, with the expected execution, and to do some tasks. For example, first, try to discover from event logs process model. Second, we try to do conformance, so to see if these event logs are compliant with the process model. Third one, it tries to do enhancement, so to enhance the process model on the basis of real process execution. Event logs have this format. The idea is that an event log is a log composed by a certain number of cases. So each one of these boxes is a case. A case is a single execution of a process model. So it's a single run of the system. Each case each row of each case is an event. An event is an activity executed with some information associated with this activity. For example, timestamp, data, the resource that execute activity, and so on. So the idea is that to each event we can associate an activity of the process that is being executed. And each case in process mining is called a trace. So a trace represents a single run of a process model, a single process instance executed in the real world. Okay? Okay, the problem that we try to solve in this paper is called trace alignment. This trace alignment is born by the fact that process models are typically not enforced by information system, because during the execution process there is a lot, let's say, of human behavior that is involved. So the fact is that these traces that represent the real execution of process usually are dirty. So they contain, for example, missing events, they contain more events that are useless, they are spurious, and so on. So we have a discrepancy between the expected process behavior, the process model, and the real process behavior, so the event logs. The trace alignment lies under the umbrella of conformal checking. Conformal checking is one of the three kinds of process mining, and is the problem of cleaning these traces against process model with three purposes. First of all, to understand if a trace is compliant with the process model. Second task is to identify the root and the severity of each deviation. And the third task, that is the one that we are focusing now, is to repair the trace to make it compliant with the process model. To repair a trace means to take a trace, to see if it is compliant, and if it is not compliant, to add or remove activities to the trace to make it compliant with the process model. So basically this is the idea of trace alignment. In this particular work, we try to solve this problem by exploiting planning technologies. So planning technology, in particular state-of-the-art planning systems. In particular, we have focused on the state-of-the-art declarative process modeling language. This state-of-the-art process modeling language is called Declare. Declare consists of a set of activities and a set of constraints by OD that are constraints on such activity. These constraints in Declare are instantiation of so-called templates. So a template in Declare is a pattern that defines parameterized class of property. Templates in Declare have a graphical representation, so we can graphically represent the constraints of the model and enjoy precise semantics in LTL on finite traces. Okay? LTL is linear temporal logic. I think that to this audience I don't have to explain what LTL is. So the important is to say that LTL, traditional LTL interpretation of traditional LTL is done over infinite traces. Otherwise, in our study, in the business process management field, we use LTL-F. So LTL interpreted over finite traces. Okay, otherwise the problem will not be decidable. Okay? Why that? Because our traces are finite and the constraints of our Declare model are finite. Okay? So we use LTL-F. I show you now some template of this Declare process modeling language. For example, the existing template the graphical is this one. The LTL formalization of this template is eventually A. So this template means, okay, we have a trace, at least one instance of A eventually appears in the trace. So for example, this trace BCAAC is compliant with this constraint because an A appears. This third trace BCC is not compliant because no A appears in the trace and this constraint is violated. Okay? There exists a lot of templates. I'd like to show you another couple of ones. For example, response AB. The LTL formalization of this template is globally A implies eventually B. So basically it means that when an instance of A appears in the trace, an instance of B must appear after A somewhere. Okay? So for example, this first trace, BCAAC, is not compliant with the response because we have some A here but no B after A. This second one, CACB, is compliant because after the first instance of A we have a B and after the second instance of A we have the same B. So let's say the constraint is satisfied. Okay? Other one, the last one, chain response. Globally, A implies next B, so in this case it means that every time that A appears, I want a B directly after A. And for example here, this third trace, BCABABC is compliant because we have a B after each A. And these other two are not compliant because, for example, this second one, because we have BCAABC, so after the first A, we we should have another bit to make the trace compliant with the chain response template. So the idea is that the Declare model, process modeling language, provides a certain number of templates defined over LTL to, let's say, implicitly specify the order of activities in the process model. This is very different from the imperative models, where we explicitly specify this order. Here the order is implicitly specified by constraints. Okay. Now, our problem is to encode trace alignment, so the problem of aligning the trace with respect to the declarative process model. And in particular, for doing that, first of all, we define a single planning domain that is able to encode the Declare model and the event log. Secondly, we define for any trace contained in the log, so because a log can contain a certain number of traces, usually thousands of traces, for every trace in the log, we define a planning problem. Okay, so we have a single planning domain that is valid for the entire Declare model and for the entire log, and for any trace, we define a single planning problem. We feed a state-of-the-art planner with above inputs, and the idea is that for any trace, we are able to synthesize a line that is a sequence of alignment steps that can change the original trace, TDI, in a new aligned trace, TDI prime. Okay? Basically, the plan consists of a certain number of add and remove actions to modify the original trace by obtaining the aligned one. It is clear that if a trace is already compliant with the Declare model, the plan will be empty. Okay, so that means that the trace has been is compliant. We can also quantify the severity of a deviation between the trace and the model, and for doing that we use a cost function on the alignment steps. For example, it may be more costly to skip an insurance check for high claims than for low claims. So we can give a weight to every deviation, to every adding or removing action that we want to perform on the original trace. Our encoding in particular is based on PODL 2.2 because we need the derived predicate and we need the action cost requirement to, let's say, keep track of the cost of planning actions. Now, let's give a glance to our encoding. And to do that, let's take this running example. So here, the running example is very simple, it's just to understand encoding. So we have a simple Declare model that is composed just by two constraints, existence of A and chain response AB. And the log that is composed just by one trace, A, B, A, C. Notice that in the trace, each activity can appear more than once. So we have each activity can have more instances of it inside the trace itself. Okay, first of all, we need to define a unique abstract type that is called activity, so for defining every kind of activity contained in the trace, and several subtypes to define the specific kinds of activities that we want to keep trace. For example, in this case we have A, B, A, C, so we have three kinds of activities, A, B, and C. We need just four predicates, just for basic predicates for keeping trace of the structure of the trace. First of all, we have the predicate traced. Traced holds if an activity is included in the trace to be aligned. We have other two predicates called first and last that are very simple, very trivial. They hold if the activity is the first or if it is the last activity of the trace. And we have an important predicate that is called succession that is used to, let's say, to build the structure of the trace. So to say that an activity comes before another activity in the trace. With a list of SAC, with a list of these predicates, we are able to, let's say, to represent, to emulate, to simulate the structure of the trace. All the constraints of the Declare model are represented through the derived predicates. So for any constraint, we have a different derived predicate that expresses that constraint. For example, existence of A, we are defining a derived predicate where we say that these constraints holds if exists an instance of kind A such that that instance is in the trace, so it's traced. Okay? For example, the derived predicate for the chain response is saying that for any instance of A, of kind A, this constraint is valid or if that distance is not traced. Because if there is no A in the trace, this constraint is already valid. Otherwise, it is valid if exists another instance of kind B such that A precedes B. Okay? So any declared constraint can be translated in a proper derived predicate. Clearly, we have also more complex derived predicates, for example, the response. Now, I do not explain the response, but it can happen that some constraint require nested derived predicate for, let's say, for being encoded. Okay? What about planning action? We need 8 planning actions for doing trace alignment. In particular, our planning actions are able to add an activity to an empty trace, remove an activity from a trace of length 1, add remove an activity from the first or the last position of a non-empty trace, or add remove an activity between other existing activities that are already included in the trace. Okay? So basically, the main actions are to add and remove, but we have to, let's say, split them in more actions to add or remove activities from the various part of the trace. And this is, for example, the encoding of a particular action add between that is in charge of inserting an activity between other 2 activities. An important aspect is that for any add or removal activity, we specify the cost of adding or removing that activity instance in the trace. Okay? What about the planning problem? For the planning problem, clearly we have first of all to define the number of objects that we need for doing trace alignment. So the idea is that the number of objects depends by the number of instances that can be used for doing trace alignment. For calculating this number of instances, first of all, we take all the instances that already exist in the trace. So in this case, A0, A1, B0, and C0. But the problem is that if the trace don't conform to the declared model, we can need additional instances of activities that can be required for the alignment. But we have to calculate how many instances we need in the worst case for doing the trace alignment with the planning. For solving this question, for answering this question, we calculate the number of these additional instances by calculating a constraint satisfaction problem. This problem considers the initial number of each activity instance in the trace to be aligned and a certain number of inequality constraints as the declared constraints. I have no time to explain this, so you have to trust me. The idea is that with this constraint satisfaction problem, we can understand the worst number of activity instances needed for align a trace in any way. The proof is on the paper. Okay? To close with the planning problem, we have an initial state where we represent the structure of the trace and we make explicit the cost of adding and removing actions from the trace. In the goal condition, we just put the conjunction of the derived predicate that represent the constraints that we want to satisfy. So our goal condition is just a conjunction of derived predicates, exactly the constraints that are part of the model. And finally, since we want to minimize the total cost of our alignment, we also put the specification to minimize the total cost. Since I don't think I have so many time to talk, I'd like to show you, first of all, the tool that we developed. So we developed a real tool for doing that if you want later I can show you a live demo of that. And this tool is able to take in input the logs formatted with access starter. Access is the standard for representing event logs. It is able to take in input real declared models, so models defined with the declared system. So we can define graphically the model that takes it in input. This tool takes the ELP solver, LP solver to calculate the number of instances required for running a task. And finally, we make use of the fast-forward planning framework to perform the planning step. We perform some experiments with the real case study. This is a case study that comes from the personal notes in the Dutch Financial Institute. The log is quite challenging because it contains thousands of traces with thousands of events. And this is basically the declarative model that represents the process whose real execution is contained in the log. We perform an experiment, and our experiment, let's say in our experiment, we try to also study the scalability with respect of the size of the model. So the original declarative model contained 16 declarative constraints, so we synthesize more declarative constraints to see how the planner is good to solve the trace alignment problem. Again, I have no time to discuss the results. The good aspect is that with fast onward, but this result is very linked to fast onward. You can use whatever planner you want, the encoding is generous PODL. With this planner, we were able to align even the most complicated traces. So the one composed of 60 events, 60 events are a lot, so are very big processes, in no more than 10 minutes. But the good aspect is that 50% of the traces are no longer than 59 events, and 70% of the traces contain no more than 25 events. And these traces, we are able to align these traces in less than 1 minute and a half. Some other consideration is that the majority of the time happens at processing time. It is shown by the table before, basically. So we take a lot of time to build the structure, build the search structure, and very few time, milliseconds for doing the searching. So for sure we have to improve the grounding of the encoding of our tool and to improve the grounding. And clearly the tool performance decreases as the trace becomes longer, but it is interesting to see that the approach doesn't seem to degrade so much when the process model increases on size. So if we have more constraints, the performance does not degrade so much. So the performance degrades when we have a trace more long. I conclude by saying that if you are interested in this kind of studies, on this website of the Business Process Intelligence Chapter, there are real event logs. So we have real traces of execution of processes. This is a novel, let's say, this is the application planning technique has been, is not novel in BPM, but is novel in process mining, is novel in this particular field. And the results are, I want to underline, are preliminary, but are quite promising, in particular because for process mining we have to do reasoning offline, so we don't need the real-time performance. And for concluding, future work on that is that we want to extend our encoding to take care also with data and time that are in the events. This because there exists a clear model with data and time. We want to perform trace alignment against the entire LTL finite language. And we want also to customize trace synthesis for simulating process execution scenario. Sorry if I too much.
So I think we do have time for more questions. If you want to come in, maybe Jim.
Just a question. You consider duration in the model of the process?
You can. We did not consider duration, so in our case, the tasks are considered as atomic. Okay? But absolutely you can. So you can consider duration, and in particular, the nice aspect is that in the logs you have the duration of the task. So you have the information about the duration of the task. You have also information about the data used by the task and the results, for example. So you have a lot of information that can be used for doing the mining. So it can be done, basically.
First of all, I enjoyed your talk, so I really was interested. But I'm curious about what kind of process are you replacing? How is that tradition? The kind of, how it's called? Well, I don't remember, but the problem that you are now solved with blending, how is that usually? So, what kind of?
Okay, there is for imperative process models in the BPM literature, there are a plethora of approaches that do that. These are all ad hoc approaches with a lot of optimization and so on. For declarative models, there is just one approach that is able to do the same stuff that we do with planning. They do with A-star search. The problem is that, let's say, this is, let's say, one work. This work suffer if you use negative constraints. So I didn't show here that we have, in Declare, we have a lot of negative constraints to represent that an activity must not appear in the trace, for example, or rules that make explicit the fact that an activity does not appear somewhere in the action. Another aspect is that that approach, with the results, the time performance are quite comparable. Okay, they are more good with little traces. We are more good with larger traces with negative constraints. By the way, a good aspect is that that approaches are fixed, so you can use that approaches just for doing process mining on activities. So instead, this work is the base for doing process mining by taking care also that at the time. That's, let's say, the adoption of using planning in mining.
Okay, so let's thank the speaker again. Okay, so the next talk is from Andrea Brodini. So his paper's title is a planning-based architecture for recruitable manufacturing system.
Okay, thanks for the introduction. This is a joint work with several world and basically reconfigurable manufacturing systems are currently the suitable solution for facing modern manufacturing system in which often we have frequent product modifications or shorter product life cycles that require manufacturing systems to be very adaptive, very reactive, and able to minimize the stopping production. So, as been envisaged, the usage of specific reconfigurable enables that are both hardware and software technological solutions to entail and load manufacturing system with specific adaptive features that are able to face such kind of production cell. And in particular, we focus our attention on logical configurations of control that may result from the need of adjusting dynamically functionalities and control policies in order to face changes in the production plans. And model-based approach has been actually proposed in the past, but a main crucial point is that capturing in a unique model all the possible situations on the fly, managing all the possible failure of events that may happen in a specific plant remains a crucial problem. And in particular, this is a key problem when structural modifications occur, entailing a redesign or requesting a sort of redesign of control strategies and then a possible stop in the production. That, of course, is something that should be avoided. In this sense, we propose the exploitation of knowledge-based reasoning techniques to dynamically generate planning models, so to adapt online the planning model and exploit a timeline-based planning methodology to implement adaptable controllers for a configurable manufacturing system. This is the outline of the talk. Basically, I will introduce a reconfigurable manufacturing system case study elicited after a research project in which we were involved. Then I will present a planning-based architecture. This is the proposal of the main contribution of the paper, proposing the implementation of what we call a knowledge-based control loop. So the idea of managing knowledge online and dynamically adapting the control system. And this is possible exploiting knowledge representation and reasoning techniques integrated with deliberative control with timelines, and implementing the bridge through a planning model generation process that is able to exploit the knowledge reasoning, generating the control model to be enrolled in the timeline-based control system. Then I will show some experiments that we performed in order to test and demonstrate the feasibility present some ideas for future works. We were involved in this GECKO project. This was actually a national project within the Italian flagship initiative of Factories of the Future, whose aim was basically to design a generic and adaptive control infrastructure for a configurable manufacturing system. The idea is to envisage, to talk about the production plant as a community of autonomous, self-declaring, collaborating GECKO modules, where each module is encapsulated in a physical mechatronic component in the shop floor. And our idea was basically to consider individual AI-based agents reasoning on a continuously updated knowledge base representing the status of the agent and the status of the environment, in order to adapt the domain model and then plan and execute their own action facing the production nodes. In the project there was a real pilot plant that was basically an automatic shop floor system for printed circuit boards working. There were several machines for testing, for fixing, for shredding, and all the machines were connected through a reconfigurable transportation system, realizing the movement of pallets and then of PCBs to be tested and worked. And basically in our work we now focused on the transportation module, so the single component of the overall transportation system. That is the element in the plant that shows, let's say, the more capabilities in reconfiguration, physical reconfigurations, because these are two possible configurations of the transportation module. You can see there is a main conveyor that is able to implement this kind of transfer. Then you can have multiple cross-transfer units that allow side-by-side transportation of the pallets. So, according to the physical configuration, the transportation module is able to implement multiple transportation tasks. So, the planning architecture is this one. Basically, we reach this, let's say, classical planning and execution loop with a knowledge manager component that is able to create an abstract representation of the status of the mechatronic module and the environment in which the mechatronic module is told. And the knowledge-based control loop is actually working in this way. The mechatronic module is switched on, the diagnosis module performs a collection of sensor data in order to provide a first, let's say, raw abstract representation of the status of the mechatronic module and the environment. Then the knowledge manager builds a first basic abstract representation of the mechatronic component. Through a rule-based inference engine, we refine and extend such abstract representation in order to elicit the functionalities that the component is actually able to implement in the specific context and according to its physical configuration. And then we have defined a model generation process in order to dynamically update the planning domain according to the situation represented in the knowledge base. Then the classical plan and execution control loop is going on until some major reconfiguration, for instance a physical reconfiguration of the mechatronic module, a failure, whatever, is actually triggered. Then the diagnosis module is supposed to recognize such event and update the knowledge page. The inference engine is recalculating the functionalities that are actually implemented by the component, and the planning domain is actually updated. So this is the loop going on. So it's a double loop, the classical one and the knowledge-based control loop that is higher level. In designing and defining the knowledge manager component, we followed an ontology-based approach in order to support the informed control module design and classify the information that we actually need in order to face the communication and functional needs that each agent is supposed to address, and also to provide a common view of the shop floor shared among the different GECKO nodes in order to allow such modules to understand and use a common language to interact and collaborate. And of course, our goal was also to enable such automatic generation of control models that I just mentioned. In the previous work, we defined, we pursuing an ontological analysis of the information that we needed in order to represent such components and environments. We distinguished and defined different information contexts, in particular the global context shared among all the modules in order to represent, let's say, the high-level information that all the modules should know and use in order to communicate among them. An internal context containing all the information related to the specific capabilities of the agent and the structural information, the local structural information of the module, of the mechatronic module. And then a local context for a single module that is basically representing the information related to the topological connections implemented in the plant or the activity coordination and commitments that the agent is supposed to perform. Then a further contribution in this previous work was the definition of an ontology of functions in order to provide an abstract representation of all the capabilities that the mechatronic component in this kind of configurable manufacturing system can actually implement. So this is, let's say, this is a sort of abstract classification. There are different kind of functionalities that can be implemented. For instance, in the transportation module, we focus on the channel, that is the functionalities of transporting pallets, so transporting objects and changing the position in the plant. But this is a general description of the functionalities of such kind of modules. Then, the contribution of this paper is the definition of a knowledge processing mechanism in order to update and infer, update the knowledge base and infer such functionalities. The mechanism is implemented in two steps. The first step is basically exploiting the context information in order to capture the information generated by the diagnosis module in order to classify the information coming from the plant and build, let's say, the atomic representation of the component and environment. And then the second step is exploring capability inference rules that are domain-dependent, of course, and that allows, with the exploitation of the taxonomy of function, to infer the actual functionalities that the agent is able to actually implement and provide in the shop floor. So this is just a very small excerpt of the actual knowledge base that we developed for the transportation module in the pilot plant, and the dotted arrows are basically the relations inferred by the knowledge process mechanism, in particular in the second step, in order to elicit this information about the possibility to perform the channel from the port F to the port B, so the main using the main conveyor to make this kind of transportation. And as I was saying before, we pursue a timeline-based approach to planning. Basically, for the ones that never heard about this, is a different way of doing planning, focusing on some key features that represent let's say, the main behavior of the system that is supposed to be controlled. It is possible to describe the temporal behavior of the system, describing the temporal behavior of the specific features, and then represent some constraints that are supposed to represent and model the causal and temporal relation in the global behavior of the system. And the planning phase basically is constituted by the extraction of timelines for each of these features describing the system in order to enforce the achievement of the planning goals, of course, and satisfying all the model constraints that are supposed to describe the correct behavior of the system. Eliciting, leveraging the contribution, the result of the ontological analysis, we also defined a modeling approach for generating the timeline-based specification, and in particular, we defined and identified 3 different classes of state variables in order to provide a sort of methodology to model blending problem, blending domain actually. And so we distinguish between, this is a sort of parallel with the context information or information. So we have functional state variables in order to describe the main function of the modules with no consideration about its internal structure. So we just say this is what the agent is supposed to perform in the system, and then in the primitive state variables we are going to describe which are the physical and logical components that are supposed to implement the main function. So this is what we do and this is how we do. And the external state variables are actually describing elements that are, let's say, outside the control of the system. So for instance, the presence of a neighbor that is supposed to receive some pallets, or the presence of elements that are not in the direct control of the system. All these state variables are orchestrated, let's say the behavior of all these variables are orchestrated through the definition of synchronization rules that are the temporal and causal constraints among the state variables that enforce the representation and the correct behavior in the system. So here you can see this is the main, the functional variables with different channels, so the functionality of transporting the pallets considering different ports. This is the presence of the main conveyor and the two conveyors and the cross-transfer units, and this is the presence of two different labels. This is one specific possible configuration of the transportation module, and if you refer to the paper, you may find in the appendix a full example of both the knowledge base and the running model that we generated for one specific scenario. Then, recalling the main picture, we have the knowledge base representing, after the inference step, representing the status of the agent, its components, and the functionalities that are actually deployable in this specific context, in the physical context in which the mechatronic module is operating. And then we can generate the blending model, the more suitable blending model for the specific context. So this is basically the step that is connecting the knowledge manager and the deliberative controller components. Is basically implementing an analysis of the knowledge base in order to generate the blending domain for the agent. So it results to be the more suitable domain with respect to the specific situation, current situation. And this process, this is the very high-level algorithm. Again, in the paper we found appendix that's driving the whole generation process procedures. And basically this process exploits the knowledge base information and the inferred functionalities, functional capabilities of the system in order to encode this information in terms of state variables and synchronization rules according to the modeling approach that I listed before. So we performed, in order to assess and test the feasibility of this approach, we performed a set of tests with the knowledge-based control loop deployed on a single time transportation module, analyzing its performance in different module configurations, increasing its complexities. So we consider simple, single, double, and full configurations that are basically an increasing number of cross-transfers units and then an increasing number of actual functional capabilities that the agent may provide in the production plant. We envisage two dynamic reconfiguration scenarios, that is reconfiguration events that may be external, so for instance the temporal availability of one of the neighbors. So the lack of one neighbor entails that the transportation module is not able to transfer, of course, pallets to the neighbors that was able before. And internal reconfiguration scenario, in which basically we consider cross-transfer failures, so the failure of one of the cross-transfer, reducing the number of functionalities that can be actually implemented. Of course, we consider, let's say, in a very pessimistic way, only negative aspects, but we can also consider a reconfiguration scenario in which something is added. So, for instance, we can envisage that a new cross-transfer unit that and so the functional capabilities is increased. So the reconfiguration in our approach is indifferent in this way. So we consider different issues while performing our test. We consider the knowledge processing mechanism cost, the model generation cost, and the planning cost, exploring a recent plan developed by Alessandro Murillo that is here, maybe developed by him, that is still an UP-CDRF time-based planner, compliant planner, and for what concerns the knowledge-based inference and model generation cost, basically this is the setup phase, so when the system is switched on. We have constant inference cost and a linear trend in the model generation process cost. Let's say that this is because the knowledge management tool that we're using, they are actually used to manage very huge amount of data. In this sense, in our case, we have a knowledge base that is not so wide. So this is, let's say, this is expected in some way. While here we have the combinatorial effect of an increasing number of functionalities, and that's also this result is somehow expected. In any case, please notice that the temporal, the time, and the cost are still under the almost 2 seconds and a half. So the costs are still, let's say, reasonable for us. And in the case of the reconfiguration scenarios, whatever we consider, whichever one that we defined before, the knowledge processing costs again are negligible because basically there are small modifications of the knowledge base. So again, the tools are very effective in managing and inferring the knowledge in this sense. And then basically this is okay. There is something cut here, but anyway, the point is that the knowledge processing mechanism is not crucial. The cost for that step are not crucial also in the reconfiguration step. And for each reconfiguration scenario, both given from external and internal motivation, also the model generation costs are relatively small because essentially each, in the specific case that we considered, each reconfiguration is going to reduce the number of functionalities, so the costs are more or less comparable with the one expressed in the setup phase. I'm almost finished. This is the planning time. We consider the different, again, we consider different configurations. Of course, the more complex is the planning model, and the harder is for the planner to synthesize the plan. And this is also reasonable that the planning costs for the complexity of the configurations of the transportation module. But you can see that in the more complex case, so the full configuration with 3 cross-transfer units, we have something that is following this trend. We have for 10 requests for pallet movements in 15 minutes. We have a cost that is 30 seconds. So this is something that, let's say, is okay with our requirements. In general, I can say that these results allows to say that the deployment of the knowledge-based control loop is actually feasible in the pilot plan that we considered. Okay, again, in 15 minutes we have 10 pallet requests, and we are able, with no more than 5 seconds, to manage knowledge-based issues by the knowledge manager, and no more than 50 seconds by the planner to generate a suitable plan. So the knowledge-based control loop is actually able to avoid major overhauls of the control policies, dynamically adapting the planning domain, and then addressing dynamic adaptation of the control to variation of all plant reconfigurations. To end the talk, we proposed a planning-based architecture to integrate ontological and contextual information interacting with a knowledge-based control loop, and deploying adaptive controller in a reconfigurable manufacturing system. The experimental results actually show the feasibility of this approach in the real pilot plant. And now we are working with the idea of exploring several future directions, in particular with different environments and agents in technology. And for the ones that were present at the Safe Plan workshop, now we are specifically focusing on safe human-robot collaboration situation. And that's it. Thank you.
Any questions?
You may have covered this and I missed it, but I was just curious. It looks like your triggered reconfigure is based on some kind of external intervention or some kind of failure in the manufacturing process, something like that. I was wondering, I guess my question was really, have you thought at all, or do you think this could extend to a situation where, you know, maybe you're not forced to make a reconfiguration change, but maybe you want to trade off efficiency of different configurations? You know, so it's more of a optimization kind of issue, I guess.
Let's say that in our approach, the general idea is to, okay, let's say in general, I can agree that it depends on the specific problem. So, for instance, in this specific problem, the transportation module is not so complex, considering the single agent. So there is no need maybe to, let's say, exploit such knowledge-based approach, blah, blah, blah. But in general, when you consider pilot plant or whatever plant that is composed by community with an increasing number, you have to face different I don't have the picture. In any case, consider that you may have here, you may have the actual reconfigurable transportation system that is composed by many of these modules. And in our case, if you use a physical configuration for this transportation module, we don't mind to put the topological information in an explicit way for the control in the agent, because it's the transportation module and the knowledge manager that is managing this kind of issue. In the actual plans, and actually the people working in the control level are doing this, in the control level, if you don't have this kind of feature, you have to implement it by yourself, the control, and if you change the physical configuration, you have to rewrite the control procedures, unless you have some other kind of control feature that, let's say, allow you to have a smarter control system. In this case, we are exploiting this to avoid that the controller engineers are forced to re-implement controller when, for instance, you just stop everything, switch this one off, and then we switch on. In our case, it's just to have the statical description of the topology, but then the controller is just is the knowledge manager that is managing when an agent is able to transport the pallet from a module and another. We have no need of coding anything. This is their advantage.
Any other question?
I was just wondering about the planning that is done once you have synthesized the planning model. Is that done on a distributed basis per component, or do you make a plan for the entire plant to actually output something? Or?
The planning model is, this is just an example. Basically, the planning model is related to the single agent. Of course, there is another part of the architecture that I didn't present here, that is about the coordination among different agents. So, in that case, we don't use planning for coordination, but we use an action-based techniques. And then, once the coordination step is addressed by the coordination module, let's say that each agent has a set of commitments that represent the planning goal for the single agent. So in this sense, the coordination is managed in another way, and then for us it's just a set of planning goals to be managed online.
I was wondering if you have thoughts about how scalable this is in practice. So if you increase the number of production modules to 100,000, I don't know, on the one hand, are there practical applications for such a thing? And on the other hand, what will your planning approach do? Will it compute for 3 days and come up with a solution? Will it compute forever?
Okay. There are two answers. The first answer that with the pilot plan, we were not able to test any modification because basically the pilot plan is in that configuration and we cannot change it because it's fixed, it's very complex to change anything. So we performed some tests in simulation, and I have to say that we need to perform some more extensive campaign in order to actually say that whether this approach is scalable. But in any case, in this sense, we have tested on a pilot plant that was composed by more than 30 transportation modules, 6 machines, and managing different pallets. So let's say that at least is okay for a specific production plant that is very close to actual production plants. Of course, we need to test in a more extensive way the scalability. And the other answer, sorry, can you repeat the second part? Sorry, to apply in different contexts, right?
Yeah.
So, actually, we exploit this approach, this ontological approach, in order to be as much as possible general in addressing a specific problem. So, we use ontology in order to be, again, as much as possible in the manufacturing scenario. General, so for instance, changing the production scenario, unless we are broken somewhere, this ontology is still valid. And the mechanism implemented here is dependent only from, of course, the diagnosis module that, of course, should be domain dependent. The rules defined here that, of course, are supposed to be domain dependent. And then all the other steps, okay, also the service, sorry. And then all the other steps are somehow domain independent as much as possible. But the idea is that we are, of course, it is very challenging, no? So actually, I can say that here there are some steps that are, of course, customized for the specific case. But in general, the general infrastructure, the general approach, our challenge is to say that it's actually general, and we want to demonstrate that. Of course, this is not a demonstration of the generality of the architecture, but our aim, our long-term goal is to demonstrate the generality of the architecture.
Okay, so let's thank the speaker again. Apparently, the last talk of this section, the speaker is not here, unless you're hiding. No. So yeah, we won't have this last talk then. So that means this is the end of this is a manufacturing application session. Just a quick reminder, the lunch is supposed to start at 12:30 and then to 10 to 2 p.m. And then we start the outstanding paper sessions. Pretty good. So thank you everyone for coming. I appreciate it.